Dr. Elishakoff, you are rolling. You may proceed, sir.
Thank you so much. What is our topic number? Vibrations of inhomogeneous beings. So, governing equation is like this. d2 dx squared d of x d2 small w dx squared plus rho a d2 w dt square equals 0. And d of x equals exi. So inhomogeneity means e of x or I of x or rho of x and a of x. If any of these quantities is not constant, is a non-constant, we have an inhomogeneous.
Doctor, we need your mic on, sir.
Mic is on. It is on. Yes, it says on. No, it's a green light. We have an inhomogeneous being. So, or when we substitute small xt equals capital W of x and then sine omega t, where omega is a natural frequency. So we get the following then. d2 dx squared d of x d2 capital W dx squared minus rho a omega squared. W equals 0. Now, direct problem is what? D of x is given, rho a is given, find omega squared. So that is very difficult to solve. No general method. No general method is available. Okay, usually special functions or approximations. Galerkin, FEM, etc. Okay. Special functions or approximations, Galerkin, finite element method, or other methods. We use semi-inverse method. That means half inverse. Just before that, what would be the inverse problem? Inverse problem is like this. We know omega 1, omega 2, omega 3, etc. Find d of x and rho a of x. That is an inverse problem. So that means that we know measurements of natural frequencies. So there is a very interesting result. Interesting theoretical result. Yes, name is Barcelon V. Title, Inverse Problem of a Vibrating Beam. Journal of Applied Mathematics and Physics. Volume 27, pages 347, 358, 1976. So this interesting result is as follows. You may want to write down this result. It is not enough to know all infinite amount of natural frequencies. To reconstruct d of x and rho a. Not enough. So what is needed to know is as follows. It is needed to know infinite amount of frequencies. Of the beam in two boundary conditions. Boundary conditions. Say simply supported, and then clamped. So we need here infinite amount of frequencies, means omega 1, omega 2, etc. Here we need omega 1, omega 2, etc. Then we can find. So that means that this inverse problem is very restrictive. Inverse problem's solution is very restrictive. Why? Because who will give us 2 times infinite number of frequencies? Okay, I wrote to someone like this who deals with such inverse problems. How can we visualize this? So we can say that there is one planet, that is planet Earth, and we are here. And then there is another planet, and in the another planet there is someone else. And here he has a beam. Now, this person, okay, so we are helping. We know how to solve the problem. So he has to measure actually frequencies simply supported, omega 1, omega 2, etc., many omegas. Then for clamped. Then he has to pass this information. Then we will tell him how much is rho A equals this, and d of x is. So it is a very artificial imagining of the situation. Because if I know infinite amount of frequencies, probably I could also just measure d of x. I mean, to find natural frequencies, so many, is much more difficult than to just check, this d of x, look at the beam and measure what is happening. So it's appears to be very artificial. Okay? So direct problem. Impossible to solve. In general. Inverse problem. Okay, impossible to visualize. Means, of course, that is very difficult also once you have all the natural frequencies, what to do, how to do, etc. So we are suggesting semi-inverse problem. Semi-inverse means we don't know omega 1, omega 2, etc. We know some, for example, fundamental mode shape, psi of x, as before. So then we have like this. So we postulate knowledge of psi of x or psi of xi. Okay. Okay, I'm not finding that. Okay, we will deal with it. So what we have then is as follows. We have d2 dx squared, then will be d2 psi dx squared minus rho a, d of x, minus rho a psi equals 0. So we introduce again our x over L equals psi. So then we have 1 over L squared d2 d psi squared d of psi 1 over L squared d2 psi d psi squared minus rho a psi equals 0. Or finally we get like this. d2 d psi square d of psi d2 psi d psi square minus rho a L in force power psi equals 0. Now this is a fourth order polynomial. Now this is also fourth order polynomial and there are 4 derivatives. So therefore this thing to be fourth order polynomial, this guy should be fourth order polynomial. Pay attention, in buckling we had second order polynomial d of psi. In buckling under the concentrated load. Then under distributed load we had third order polynomial. Now this is vibration, we have fourth order polynomial. So therefore d of psi equals b0 plus b1 psi plus b2 psi cubed plus b4 psi in fourth power. Psi of psi, so it is simply supported, equals psi minus 2 psi cubed plus psi in fourth power. Can you say? No, psi square will be for clamped. And this is for simply supported, is just psi. Oh, here. Oh, b2 psi square plus b3 psi cubed plus b4 psi in fourth. Yes, thank you. So then minus rho a. Oh, but I forgot here else omega square. Pay attention here. Minus rho a L in fourth power omega square psi equals minus rho a L in fourth power omega square psi, which is psi minus 2 psi cubed plus psi in fourth power. Now we start here to deal. So psi's first derivative is 1 minus 6 psi squared plus 4 psi cubed. Second derivative equals minus 12 psi plus 12 psi squared. Or it is 12 minus psi plus psi squared. Now we have to multiply this with d. So d of psi second derivative, this equals b0 plus b1 psi plus b2 psi squared plus b3 psi cubed plus b4 psi in fourth power 12 minus psi plus psi squared. Now this equals 12, of course, and then we start. So b0 times psi minus b0 psi. And I multiply. Then let us do with psi squared and plus psi squared. Psi squared will be obtained when this psi is multiplied by this. So minus b1 plus psi square when psi square is multiplied by b0. Then psi cubed. Psi cubed is obtained when minus psi is multiplied by this. Minus b2 plus Psi square is multiplied by this one will be B1. That is psi cubed plus psi in fourth power. Psi in fourth power when this is multiplied by this will be minus B3 plus psi square by psi, B2 psi square plus psi in fifth power when this is multiplied by this minus B4 plus this multiplied by this plus B3 psi in fifth power. And then there is B4 psi in sixth power. Now I have to differentiate. D of psi 2 first derivative will be 12 minus B0 plus minus B1, so that is 2 here, plus B0 psi plus 3 minus B2 plus B1 psi square plus 4 minus B3 plus B2 psi cubed plus 5 minus B4 plus B3 psi in fourth power plus 6 B4 psi 5. Now we again differentiate. Minus 12. This is 2 minus B1 plus B0 plus 6 minus B2 plus B1 psi plus 12 minus B3 plus B2 psi square plus 20 minus B4 plus B3 psi cubed plus 30 B4 psi in fourth power. Yes? Oh, plus. Thank you. I looked at this. And sorry. So now we have to add here plus that expression that we had here. This one. So then it is minus rho A L in fourth power omega squared psi minus 2 psi cubed plus psi in fourth power. This equals 0, and this should be taken out. So now we have this expression. Okay? Now we have to diligently evaluate everything. So psi in fourth power. Let us start with psi in fourth power. Will be 12 times 30 B4 psi in fourth power. Then minus rho A L in fourth power omega squared. This equals 0. So omega squared equals then 360 B4 divided by rho A L in fourth power. Very neat, rational expression. B4 is arbitrary. Now we go further, psi cubed. Psi cubed is here. 12 times 20 minus B4 plus B3, psi cubed. There is minus and minus, so that is plus 2 rho A L in fourth power omega squared equals 0. So that is 240 here. 240, but divided by 2 is 120. Minus 120 B4 plus 120 B3 plus rho A L in fourth power omega squared Omega square equals 360 B4 divided by rho A L in force power. This equals 0. Am I going too fast? And these are canceling each other. So we have 120 B3, and we have plus 240 B4 equals 0. So B3 equals minus 2 B4. Now psi square. Psi square is this guy, but here is no psi square. So we say minus B3 plus B2 equals 0. So B2 equals B3. So therefore it equals minus 2B4. Now we have psi. So that is 12 times 6 minus B2 plus B1. That is this guy. And psi will be minus rho A L in force power omega square equals 0. So then it is 12 times 6 minus B2 plus 12 times 6 B1 minus rho A L in force power 360 B4 divided by rho A L in force power equals 0. So we can divide by okay. So first of all, we can divide by 12. So this 12 is gone. And then it is 30 here. So then it is a minus 6B2. Sorry. So, yeah, minus 6B2, but B2 equals minus 2B4. So then it is plus 12B4. Then plus 6B1, then minus 30B4 equals 0. So then 6B1 equals 18B4. B1 equals 3B4. Say it again. B1 equals 3B4. Then we have psi in zeroth power. Psi in zeroth power is this one. And there is here nothing. So minus B1 plus B0 equals 0. So B0 equals B1 equals 3B4. So we summarize then. B0 equals B1 equals 3B4. And then B2 equals B3 equals minus 2B4. So then we have D of psi equals B0, which is 3B4, plus B1, 3B4 psi, plus B1, B2, minus 2B4 psi squared, minus 2B4 psi cubed, plus B4 psi in force power. So D of psi equals B4, 3 plus 3 psi, minus 2 psi squared, minus 2 psi cubed, plus psi in force So an omega square, as we said, equals 360 B4 divided by rho A L in fourth power. Just let us have a look how this d of psi looks like. D of 0 equals 3b4. So therefore, omega square, first of all, can be written 120 d of 0 divided by rho A L in fourth power. Can be written like this. Then d of psi can be written, we are taking out this 3b4 equals d of 0. And it is 1 plus psi minus 2/3 psi squared minus 2/3 psi cubed plus 1/3 psi in fourth power. Now, d of psi, how does it look? At 0, as we said, equals 1, 2, 3. So 3b4. At 1, it equals, psi equals 1. 3 plus 3 is 6, minus 2 is 4, minus 2 is 2, plus 1 is 3. Also 3. Now let us see in the middle, 0.5. So that will be 3 plus 3 halves minus 2 fourths minus 2 eighths plus 1 16th equals 16. 48 plus 8 times 3 is 24 minus 8 minus 4 plus 1. So that is, why did I write? Yeah, that is plus. So that is 72 minus 8 minus 12 is 61 over 16. Okay, it's bigger than 3, something like that. So this value equals 61 over 16 B4. And now, I think that I should say that the unbelievable thing is the same psi for buckling under concentrated load under distributed load and for vibrations. And all yield very neat results. So this is actually the first ever closed form solution. In the literature. For inhomogeneous beams. Okay? Never before no one obtained any solution. In buckling, there are several solutions. Any questions? Now, further results. For clamped, we take psi equals psi square minus 2 psi cubed plus psi in fourth power. And we again obtain omega square equals 360 B4 rho A L in force power. Cramped simply supported, we take psi, whatever we take. We get omega square equals 360 B4 rho A L in force power. Yes, sir? Say it again. Here? What does it mean, what are the constant value? I don't understand. Student asks, what are the constant value? What does it mean constant value? Here? This one? Oh, here. Here? I wrote 1/2. Oh, here is in the middle. 1/2. So I said 3 plus 3/2, which means 1/2. Then 2 times 1/4. Oh, sorry. 2 times 1/4 is 2/4, and minus 2 1/2 cubed, 2/8, then 1/2 in fourth power, 1/16. So I calculated value of D in the middle. Is it, so to say, like this or like this? I wanted to know. How does beam look like? What is a D of psi? Yes, Mr. Dale.
Instead of arching up, it arches down. So instead of going this way, it's going down. Since it's
So student is asking, what happens if it arches down? It does not. As we just saw, it does not arch down.
no, is there one where is there some kind of case where instead of it arching up?
I see. A student is asking whether or not there is a case where it, so to say, arches down. I did not think about this question, so therefore I did not ask this myself. So therefore I don't know the answer. But maybe, let us say for simply supported case it doesn't. But maybe for clamp it does. Clamp. I don't know. I mean, the question is whether it is thicker in the middle or at the end. So I don't know. I did not investigate this topic. But one can just see if there is such a case. Any other questions? Okay, one can, of course, solve more difficult problems like this. 8, 9. For example, rho is a function of x. So imagine rho is 1 plus alpha x. Rho is a function of x, or x over L. So then it becomes 1 plus alpha psi. So imagine what happens in this case. d2 d psi square, d of psi, d2 psi d psi square, minus rho, which is 1 plus alpha psi, rho A, L in fourth power, omega square psi equals 0. Now this is a fourth order polynomial. So then this guy is fifth order polynomial. Now psi is fourth order polynomial. There are 4 derivatives. So therefore this should be fifth order polynomial. Solution will be like this, pay attention. So there will be then d of psi equals b0 plus b1 psi plus b2 psi squared plus b3 psi cubed plus b4 psi in fourth power, b5 psi in fifth power. So it's longer algebra. Result is also very beautiful. 504 b5 and then alpha L in fourth power, alpha A L in fourth power. Now if rho A equals, say imagine rho A equals, if rho equals, or rho A equals, so imagine alpha 0 plus alpha 1 psi plus alpha 2 psi squared. Imagine this one. Then we have 6th order polynomial. And the answer is for omega square equals 672 b6 divided by alpha 2 L in fourth power. Pay attention, it depends only on b6 and depends only upon alpha 2. If rho A equals alpha 0 plus alpha 1 psi plus alpha 2 psi squared plus alpha 3 psi cubed, then omega square equals 864 b7 divided by alpha 3 L in fourth power. Okay? 10. If it is a mth order polynomial, with rho A. Okay, because rho A is usually obtained as a result of data. And as data can be approximated a certain order of polynomial. And we know from various courses, for example, system dynamics, it can be approximated as mth order polynomial, if you want. Then we have omega square equals 12 m square plus 11m plus 30 bm plus 4 divided by alpha m L in fourth power. See, that's a general result for any order of polynomial. Indeed, let us check m equals 1. Is then omega square equals 12, 1 plus 11 plus 30, b5 divided by alpha 1 L in fourth power. So 12 times 42, b5 alpha 1. So that is 420. That is 10 times and 84. So that is 504. b5 alpha 1 L in fourth power. That is what we had, 504, you see. So all of these are particular cases of this general formula. One can derive general formula. Okay. 9. 9 will be homework assignment. Homework number 23. So I will assign you 2 homeworks. 1. Simply supported beam vibration. Check if there exists a beam with Duncan's mode shape. So let us d2 d psi square, d of psi, d2w d psi square, minus rho a omega square, L in force power psi equals 0. So this guy is a fifth order polynomial. So when I differentiate 4 times, that will be first order polynomial. So this should be the fourth order polynomial. So that is b0 plus b1 psi plus b2 psi square plus b3 psi cubed plus b4 psi in fourth power. So please check this one. Maybe there is such a beam. And second, clamped beam. Check if there exists a beam with Duncan-like fifth order polynomial mode shape. You found already Duncan-like fifth order polynomial. If you remember, you solved such a problem. 360 psi, that is a load. So psi in fourth power equals 360 psi. And you found psi. So check if this psi can serve a mode shape. Serve as a mode shape of a clamped beam. So you can use hand or maple. If you use maple, it's much easier naturally to do all these calculations and analysis, etc. Yes, I would like to distribute to you the tests and homeworks, those who did. Morris is not here. That is for you. This is for you. This is for Mr. Casey. This is Mr. Fan. This is your homework. Oh, I think you have many homeworks. And I will be sitting here and discussing these homeworks. And Flores is not here. Yeah, this you may need if you want. This you may need if you want. I mean, that was a... You could have taken that home. Do we have any questions? So these are only 2 problems. We are now, I think, specialists in semi-inverse problems also. I hope. Say it again? Yes. Yes, Mr. Srinivas. First, yes, of course. And this is the second part. Okay, I will be staying here now for the rest, and I would like to check with everyone your homeworks, how you did, because I did ask several people to resubmit, and I will explain you why they should be resubmit, what should be corrected, etc. Now our plan is, I will tell you, so this Monday we will have the second test, so please everyone come. I'm asking students who did not come also to come. And on Wednesday, I will hand you the take-home exams. I mean, take-home exams, I will bring in several exams, and you will just randomly pick. First person, of course, has much choice, and last person has just one choice. But still, it is random, because it depended on how others picked, which was random. So that is not deterministic, so to say. Any questions? I see. Will it be what? I don't think so, because there are, okay, let me answer this question first. Okay. First of all, there are various, I will pose the question first and repeat the question. Question: what happens with two material structures? Two material structures. Yes. So there could be various types of two material structures. First of all, this is sigma, this is epsilon, this is 0. There could be materials like this, bimodular materials. Bimodular. So they behave differently in tension and differently in compression. So this is tension, this is compression. So analysis is naturally very different, because we have to consider what happens when the material, say, there is a vibration, time vibration, yes? So W of t. Then in some part it is in tension, some part it is in compression, then tension, compression, etc. So there is a special theory, and there are many papers on this topic, including one paper of mine also. Then if I have concrete beam, so usually in concrete beam we have direct problems. So what does that mean? We know d of x and rho a, etc. Find omega j squared. So then it can be done. Look, as engineers, we are very pragmatic. So we can use FEM, for example, or Galerkin. Galerkin method is naturally always applicable. And we studied, at least I taught you one approximate method that can be used to any situation. Once you have to find just what are the boundary conditions. If you say, I don't know boundary conditions, so if you don't know boundary conditions, then we cannot help you. You have to know boundary conditions. You have to do some information should be given there. So then you are now whether or not semi-inverse problems can be posed. Semi-inverse with concrete. My answer is I don't know. Because, you cannot reach every problem. You have to leave problems for other people also. So if you are interested with concrete, you have to sit down and write equations and find appropriate equations and pose the question, and maybe there is an answer. Maybe you can find this. You see, necessarily what we are doing is just like spoon in ocean, spoon of water in ocean. But the rest of the ocean is always untouched. And that is very beautiful because everyone can do things. We actually did a lot of problems, so to say, whatever we could, plates, etc. And we found very nice solutions. But then other people found other solutions, went by the same method and found some very fascinating solutions. And there is plenty of possibilities for doing that. Okay. Someone will be presenting, for example, at ASME Congress in Lake Buena Vista in Orlando, Florida, some paper where he will be presenting closed form solutions based this methodology for some beams with singularities. That is the title of his paper. I don't know what he means, and I don't know what kind of, but there will be that, for example, just very, very new contribution. Any other questions? Mr. Fan, you are questionless today. I want you to ask me a question, everyone. Okay. Oh, okay. Eccentricity. Yeah, Mr. Fan says that we did not speak about eccentricity. We spoke only about the topics that we spoke about, and the rest we did not speak. And the rest is very big amount of problems, very big. Say stability. So I have a course, for example, on stability. There, I do speak about eccentricity, etc. Theory of elastic stability. My lecture notes have eccentricity. If you want, I can give you, if you want, just eccentricity. But books have this. And we did not speak about load. There is a I can tell you several problems we did not speak. So there is concentrated load, axial load, but there is transverse load also. So what happens in that case? So also we did not speak about that. We did not speak about billion topics. We only spoke about finite number of topics naturally. Mr. Watanachayan, do you have any questions? You are what? A problem. Okay, so we will stop and I will talk to you. Okay, Mr. Srinivas? Or you just asked actually a question. Okay, Miss Silanpa? No questions. Casey? Mr. Dale? Yeah, of course I should have written there X changes to Xi times L, of course. But it was just shortening. I'm saying, okay, imagine that D is given from the beginning in terms of Xi. For example, it's written there already X over L. It's a function of X over L. And it indeed makes sense to, when I'm looking for D or any physical parameter, it makes sense to search it in non-dimensional parameters. So therefore, I'm saying that it was in the beginning given in that form. Thank you. Any other question? Maybe now you have some. Mr. Srinivas, maybe you had another question. No. How did you like Maple? I mean, did you fall in love with Maple? One of you used not Maple, but MATLAB, I see. Okay, what about Maple? Do you like it? Is it an assistant or it is pain in the neck? Say it again? Oh, you are just reading only now. So you did not have a time to get acquainted, so you have no opinion. Okay. Mr. Srinivas? I see. Okay. After the course you will do that or what? When? Oh, I see. Okay. But your work does not have a software? Oh, I see. It is good to have this software. Okay, I will be staying here and answering other questions, especially